Bismillahirrahmanirrahim. Assalamualaikum and very good day to you all. In this video, we are going to talk about bushing wear. Okay, this content is taken from Mushik Lee Mechanical Engineering Design from chapter 12. Okay, in the previous video, we're talking about wear on the journal itself. Now we're talking about wear on the bushing. Okay, so you know the bushing here is, let's say this is a bushing and this is the journal. Okay, where in this bushing, what will happen when wear happen at this bushing? uh, the video on wear on journal is on sliding wear. It's already in the previous video, in the previous subtopic on chapter 12:15. Okay, consider a pin of diameter d rotating at speed and in the bushing of length l and supported by a stationary radial load F. Nominal pressure given by P equal to F over dF. Okay, so actually consider a pin. We want to make an equation for it. So we consider a pin. A pin is represent the journal. The journal is like this. Consider this is a pin or this is a journal. Okay, rotating in the speed and in the bushing L. Okay, meaning that the length of the pin and the length of the bushing is the same length. Okay, and radial load is stationary and pressure given by this equation. Okay, if you remember, this equation is actually from the equation stress. P equals to F over d over FA. Okay, and the L is an area. Okay, um, and D is revolution per minute and D is inches. Velocity is given by this equation by dn per 12. Okay, and the PV is pressure and velocity in psi feet per minute is given by this equation by Fn per 12L. And note is independent. The independent of PV is from note the independence of PV pressure velocity from general diameter. Okay, time wear equation similar to equation 1227 can be written. However, before doing so, it is important to note from equation 1228 provides nominal value of P. Figure 1229 that provides a more accurate representation of pressure distribution, which can be written as P equal to P max cos theta and theta over 2, and then this range. Okay, what does it meaning by this range? You see this range. Theta is 180 degrees. Theta over 2 is 90 degrees. Meaning that here, yeah, this is 90 degrees, this is 90 degrees. So like here, theta is within this range. Okay, you want to say like that, 90 degrees and 90 degrees. Okay, meaning it's like a partial bearing. If I can sketch like this, both are 90 degrees. This is theta. Okay, theta. Okay. So pressure distribution is within this range. This pressure distribution is within this range. It cannot be outside of the range, meaning that it is most likely is a partial bearing. If you can Google the images for partial bearing, it's like this. Okay, vertical component of PDA is cos theta and this equation, and cos integrating from this, you get this equation P max equal to P or 4F by dl. Okay, and then this is the pressure distribution on a boundary lubricated bearing. Okay, this has been explained in the first video when we are talking about hydrodynamic theory from Buckham Tower theory. Okay, so you see the pressure distribution is high at at the center of it. Okay, and become lower of at the center, at the side. So I explain in that video. Also I explain here. Let's say we drill a hole here, and then we put something to plug in the screw, plug in the hole. Okay, the pressure so high at this range. Okay, and uh, it will the screw will fly away. Okay, the screw will thrown away because of the high pressure. And then this is the pressure at this point is high. The side point, the is not that high. Okay, so trade off substituting V from equation give W equal to F1 F2 K, and then this equation F1 F2 K F and T 3L. May I remind you, W in this subtopic means where. W in other topic means radial velocity. So the way that you learn, when you meet the symbol, pronounce it as a full name. Okay? You say when you are study, you say W where, not W radial velocity. Not don't just mention W. Mention its full name. Where equals to F1 environmental factor, F2 load modification factor, K is what? Uh, K is a factor also. F force, N is the revolution, T is the time, 3 L. L is the length of the bushing. Say it in full name. In the long run, you will remember. Okay, in designing a bushing, because of trade-off, it is recommended that the length diameter ratio to be in range, this range. Length over D ratio is within this range. Length, diameter, length, length, diameter. You divide it and you get this ratio. It should be within this range. Okay. Okay. Now we do the example. The OIS SP 500 alloy brass bushing in 1 inch long with a 1 inch bore operates in a clean environment of 70 Fahrenheit. The allowable wear without loss function is 0.005 inch. Radial load is 700 pound. Peripheral velocity is 33 feet per minute. Estimate the number of revolution for radial wear to be 0.005 inch. Okay, we see figure 1240 and figure and table 1212 from manufacturer. Okay, now you see 1240. This is the picture of the bushing. Okay, remember this shaft, it has a shoulder, like we have studied in a video on shaft. The function of a shoulder is to reduce vibration. Okay, and then this the load, meaning that the weight of the shaft is 700 pound, and the diameter is 1 inch. The bushing, the length is 1 inch. So this is table 1212, the service range, the units, the allowable uh, pressure, okay, allowable velocity, psi, and everything. This is the properties, tensile length equation, and everything. Okay. So this is a solution from table 12.8. K equals to 0.6 each. Table 12.10, 12.11, F1 equals to 1.3, F2 equals to 1, table 12.12, PB equals to this, okay? And then you get P max, okay? Then you check with whether it is within capacity or not. 3560 is taken from the previous table. You can pause this video, you go back to the table, the slide before this. Okay, make sure it does not exceeding the range. Okay, so 891 is below the range. Okay, so P is this equation 700 psi, V is 33, also within the range. Okay, below the range, so VB equals to me, and also below the range. You can get the equation, and for the wear. This is the table 12, the motion related factor. Okay, this is the motion related factor, whether it is a rotary, whether it is escalatory or reciprocating. Rotary, you moving like this. Okay, normal moving. Oscillatory, if you see the graph will become a sinus graph. And sinus graph. You can Google sinus graph. What is a sinus graph? And reciprocating is going like that. Okay, it's going like that, meaning that maybe this function is the journal is like, say you drive a car, the car lot of potholes, then your car vibrate all the time, vibrate all the time. Okay, your all the elements in your car will be reciprocating, up down, up down, because you are driving in the road that have many holes. Okay, so your car jump out inside the holes. Okay, so this is reciprocating. Okay, so 1211 is the environmental factor F2, ambient temperature, foreign matter, or no foreign matter. What is a foreign matter? Foreign matter is like a dust particle, the sand, and everything. Okay, this is the foreign matter. Okay, and then you check the temperature, whether it is an ambient temperature or not ambient temperature, or temperature is high. This is the F1, F2 for it. And then you put in the equation and you get the time equals to uh, 2180 hours, and the rotational speed is 126, and cycles is this 1.65 revolution, meaning that after exceeding this time you should do maintenance. Okay, then this is the way maintenance engineer can calculate. Okay, you already know when the machine must be maintained, and when it maintenance time come, they will calculate that to 180. How many days? How many days? Divide by 24. You will know how many days. Okay, and then after the day come, do maintenance to that machine. This is the way maintenance engineer do their job. Okay, so we will continue with the last video on temperature rise. Okay, thank you very much.